Okay, now let us solve few examples. Let's say first example. Question is the inside cylinder locomotive has its cylinder center lines 0.7 meter apart, and has a stroke of and has a stroke of 0.6 meter. The rotating masses per cylinder are equivalent to 150 kg at the crank pin, and the reciprocating masses per cylinder is let's say 180 kg. The wheel center lines are center lines are 1.5 meter apart. Okay, the cranks are at right angles. The cranks are at right angle. The whole of the rotating and two-third of reciprocating masses are to be balanced by masses placed at a radius of 0.6 meter. Find the magnitude and direction of balancing masses. The fluctuation in rail pressure rail pressure under one wheel, then variation of tractive effort, okay, variation of tractive effort and magnitude of swaying couple at the crank speed of 300 rpm. Okay, now we have the given data. Distance of cylinder center lines, is equal to 0.7 meter stroke length is 0.6 meter and hello how चलची नोट लेक्चर चलची okay, stroke length is 0.6 meter. Then rotating mass M1 is 150 kg. Reciprocating mass M2 is 180 kg. Fraction C is 2/3 and RB equal to RC 0.3 meter. Okay, and the distance LB is equal to LC or 0.6 meter and your RA is equal to RD or 0.6 meter. Speed N is 300 rpm, so we have omega is 2 pi into 300 by 60, so 31.42 radian per second, you can say. And then the arrangement is something like this. We have the wheels, one is here, let's say, another is here. Cylinders, two cylinders are there. A, B, C and D. So these two are the wheels and these two are the cylinder. The distance between them are 0.4 meter, 0.5 7 meter 0.4 meter. Total is 1.5 meter. Total is 1.5. Now the angular position between them, let's say one cylinder is here at a horizontal position, another is at right angle to each other, so C will be here, okay, and let's say A is here at a angle of theta A from the horizontal, and let's say it will be dotted. D is somewhere here at an angle theta D. Okay. Now next task is to draw the table as we have already discussed. So first column is your plane, then mass in kg, then radius r in meter, then centrifugal force divided by omega square, that is m dot r in kg meter, then distance from reference plane in meter, then we have m r dot l, okay, kg meter square, So let's say we have plane A, this is the reference plane, then plane B, C and D. Okay. So let's say this is mass MA, this is 270 kg, this is mass MB, and distance is radius is 0.6, here also it is 0.6 for the wheel, here it is 0.3 meter, so we'll have 0.6 MA and 0.6 MD here, and this will be 81 kg meter, and distance from reference plane, it will be 0 because it itself is the reference plane, and this distance is 0.4, 1.1, 1.5 meter, so this will be 0 and this will be 32.4 kg meter square, okay. This will be 89.1 kg meter square, and this will be 0.9 MD. Okay. Now the first step 1, we will go step by step to solve this. Step 1 is draw the space diagram. To indicate to indicate the position of planes, of wheels and cylinder. This we have already done. Step 2, tabulate the data. This we have already done. Then step 3, draw the couple polygon. Considering column 6, okay, with some suitable scale. Okay, so we'll take this reference as, let's say, O dash, it is positive and parallel to the direction of plane B. So we'll choose horizontal. So this value is 32.4 kg meter square. Then we'll obtain the point B dash. Okay, then the second cylinder is perpendicular to the first one and the value is 89.1 kg meter square. Then we'll obtain C dash. Okay, now we'll have this closing side. Okay, so this closing side you measure it, okay, which should be equal to 0.9 of MD. Okay. Now once you measure it, you will get the value of MD. So you can find out MD. In the next step, the step 4, okay, consider column 4, okay, and follow the procedure. To draw the force polygon. Okay, and you will find MA. Okay, so in this way we can solve. Now let's say we have another example. Okay, example 2. A rotating shaft, you can say, rotating shaft carries 4 unbalanced masses, let's say 18 kg, 14 kg, 16 kg and 12 kg. Okay, 12 kg at radius of 5 centimeter, 6 centimeter, 7 centimeter and 6 centimeter respectively. respectively. Okay. The second, third, and fourth masses are revolving in planes in planes 8 centimeter, 16 centimeter and 28 centimeter respectively measured from the plane of first mass and are angularly located at 60 degree, 135 degree, 270 degree respectively. Measured anti-clockwise from first mass. Okay. The shaft is dynamically balanced by two masses both located at 5 centimeter ready and revolving in plane midway between that of first and second and midway between third and fourth. Okay. Determine graphically the magnitude and position of balancing masses. Okay. So the space diagram will be like this. One, then we have 2, 3 and 4. Okay. 1, 2, 3 and 4. The balancing masses, first is, let's say it is here, balancing mass A between 1 and 2, and the second balancing mass is between plane 3 and 4. Okay. Now let's say RP, this is our reference plane. Okay. So this distance is 4 centimeter. Distance between plane 1 and 2 is 8 centimeter. Okay. Distance between plane 1 and 3 is 16 centimeter. Okay. Distance between plane 1 and 4 is 28 centimeter. And the angular positions are, plane 1 is here, okay, with mass 1, then 2 is here at 60 degree, then mass 3, this is 1, 2, 3, this angle is 60 degree, this angle is 135 degree, and this is 4 at 270 degree. Okay. This is the space diagram. Now we will draw the table. Okay. We will have here the plane, mass m in kg, then the radius r in meter, then the centrifugal force divided by omega square, that is m dot r in meter, then the distance from reference plane in meter, then we have the couple divided by omega square, okay, that is m dot r dot l in kg meter square. We have plane 1, then plane A, then plane 2, okay, then plane 3, then plane B, then plane 4. So table is completed. Now substituting the values here, let's say it is 18 kg is given, here it is MA 14, 16, MB 12, this is 0.05 meter, 0.05, 0.06 meter, 0.07, then this is also 0.05 meter, this is 0.06 meter. Okay. So this value will be 0.9, this is 0.05 MA, this is 0.84 kg meter, will be kg meter, and this will be 1.12 kg meter, this is 0.05 MB kg meter, 0.72 kg meter. Now the distance from T, plane 1 is at 0.04 meter minus, because it is towards the left, this is 0, then this is 0.04, then 0.12, 0.18 meter, 0.24 meter. So this value is 0.036 kg meter square, 0.0336, 0.1344, 0.009 MB, 0.1728. Okay, the table is completed. Now the next step is to draw the couple polygon. So take a reference point, let's say it is O dash, and will go horizontally towards left. Okay, this will be A dash. Okay, value is 0.036 horizontal because it is parallel to the plane 1, and negative because it is towards the left side of the reference plane. Then we will have the B dash, that is 0.0336. Then we will have this C dash. Okay, it is 0.1344. Okay, then we will have this point D dash, and this value is 0.1728. Then finally close the side. So this value is 0.009 MB, this one. So now you can measure this distance. Measure O dash, D dash as per scale and find this MB. Okay, it will be approximately equal to 13.34 kg. You can find this. Okay. Now the next step is draw the force polygon. Now let's take a reference point as O. Draw this 0.9, you will get point A. Then from point A take 0.84, it reach at point B. Then from point B take 1.12, you will reach at point C. Then from C draw 0.72 will reach point D, then take this point E for 0.05 MB that we have already obtained from the couple polygon. Now you join these 2 points. Okay. So this will give you 0.05 MA. So now measure OE, that is equal to 0.05 MA, and you can find out the value of MA as approximately 31.5 kg. Okay. So likewise you can solve problems related to balancing.